Hello everyone, welcome to my number theory lecture. In this lecture, we study linear combination, but before we get to that, uh, when I was, you know, uh, doing lecture two, I realized that there's something I misspoke about. Okay, so I want to correct that first before we move on to our new topic, linear combinations. So let me get to this is the part where I misspoke, right? This is part of it. My lecture two slide, my lecture two slides. So here's the theorem. Given integers a not equal to 0 and b not equal to 0 and m, if a divides m and b divides m, then the least common multiple of a and b also divides m. And then, I just mentioned that this theorem, okay, right, yeah, this theorem and also preceding corollary, let me get to that. It's about the here it is, right? So if D is any common divisor of A and B, not both of which are zero, then this common divisor of A and B divides the greatest common multiple. I'm sorry, the greatest common divisor of A and B. In fact, we proved this, right? I mentioned about this theorem, right? The Bezo's lemma. In fact, uh, in my first lecture, lecture one of number theory, and I just mentioned it, this Bezo's lemma there, and then they use that to show this corollary. So I proved it there. Anyway, so this corollary and this theorem, these are dual to each other. And then what I said, when I was doing lecture two was that, so you can get, the one from another, like by just switching like inequality. That's where I misspoke. That's what I misspoke about, right? It's more than just inequality, right? What I said is can be true for certain like ordered structures, right? So there is an ordered structure, so a set with an order. I'm not going to delve into that, but there's a statement. You can get dual statement by reversing the inequality, actually the order, okay, by reversing the order. But these are not those. So this theorem actually requires a set, a proof, okay, which I skipped last time. So anyway, so I'm sorry about the the confusion, and I'm going to go ahead and prove this theorem, and then we're going to move on to our new topic, linear combination. All right, so for that, I'm going to actually I think I can close this now. So there was a, 'a, lecture. 'a, 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 2, theorem 7, okay? I think it had a theorem number. Did it? Well, I'm not so sure, okay? So theorem, let me just call it theorem. Theorem, right. So given integers, a not equal to 0 and b not equal to 0. So a and b are non-zero integers and m, another integer m, if a divides m and b divides m. So in other words, m is a common multiple of a and b. In the case, then the least common multiple of a and b must also divide m. Okay, right. So let's prove this. So we're going to prove this actually by contradiction. Okay, one of the common techniques of proofs in mathematics. Okay, so what I mean by that is what we are trying to prove is what, under these assumptions. Okay, under the assumption, right, we want to show that the least common multiple of a and b divides m. So we start with it by, the assuming the negation, okay, negation of this statement. Okay, so what I mean by that is the negation of the least common multiple. Excuse me. Divides m. Negation is least common multiple does not divide m. And then we get a contradiction. The contradiction comes from our assumption, right? Negation of this. Therefore, it must be true, right? So that's where we are heading at. Okay, so suppose, right? Suppose that. So we are assuming everything else, okay, as written in the statement, but we are assuming that the least common multiple of a and b does not divide m. What that means is then in other words, m over the least common multiple of ab is not an integer. So when you actually divide the m by the least common multiple, in this case, you will find what is that? So there exists, right, there exist two integers q and r such that m is written as the least common multiple of a and b times q plus r, where from the division algorithm, we know that r has to be greater than 0. In this case, we know, by our assumption, right? So, m over the least common multiple of a and b is not an integer, so r has to be strictly greater than 0 and strictly less than the least common multiple of ab. Okay, so we got that. This is nothing other than just applying the division algorithm, right? Okay, now we are going to solve this guy here for r. Okay, so here we have r equals then m minus the least common multiple of ab times q. Okay, right. So that this implies, right, implies this. All right. So since in this case, since a divides m, right? A divides m. That's by the assumption. A divides m, and also a divides obviously the least common multiple of a and b. So a divides m, a divides this guy. So a must divide r, right? A must divide r. Okay, similarly, or by the same argument, what I mean by that is, again, by assumption, b divides m, and also b divides the least common multiple of a and b, right? B must divide also r. Okay, b must divide r. So by the same argument with b, actually, right, we get this one too. So what do we have here? Okay, this means r. So this means that r is a common multiple, a common multiple of a and b. So the least common multiple of a and b must be less than or equal to r. Okay, this is a contradiction. Okay, so I'm going to use I'm going to use red color. How about that? Okay, so this is a symbol I'm using for a contradiction. Okay, a contradiction. But this is first time I'm using it, so I'm gonna write it down. A contradiction. Okay, that's a contradiction. Okay, Therefore, where this contradiction happens, why is it contradiction, by the way? Here, we already know that R has to be strictly less than, the least common multiple of AB from this division algorithm, okay, application of a division algorithm. But we ended up getting the list of common multiple of A and B is less than or equal to R. So these are contradicting each other, right? And that happens because of this assumption. So that assumption was incorrect. And so the other possibility is what? This. Therefore, so this is proof by a contradiction. Therefore, the greatest common multiple of A and B must divide M. That's the only other possibility. Okay, so that's the end of the proof. Okay, that's the end of the proof. Okay, right. So now I think I cleared up everything. So that I misspoke about, and so we are ready to move on to, start our new topic. Okay, so in this lecture we study linear combinations. Okay, right. So there's a lot to talk about linear combinations. First, I'm going to start with the following theorem. Given integers a, b, and c, so three integers a, b, and c, with a and b not both equal to 0, there exist two integers x and y such that ax plus by equals c if and only if the greatest common divisor of a and b divides c. Okay? And the proof of this theorem is not actually difficult at all. I think I talked about that when I was, doing lecture 2. Okay, in fact, I talked about this theorem, and also I gave you some hint as to how you prove this theorem, right? So anyway, this is left an exercise. In fact, it is part of number theory problem set 2, number 4. And here, this number theory problem set 2 is hyperlinked. So, you just click on it and it'll take you there. And also at the end of my lecture slides, I also listed the URL with the, hyperlink. Okay, right. Corollary, let a and b be integers, then there exist two integers x, y, and z such that ax plus by equals 1 if and only if the greatest common divisor of a and b is equal to 1. In other words, a and b are relatively prime. And actually, there is nothing to prove this corollary. It immediately follows from the preceding theorem. Okay, right. So you would clearly see that. Okay, so let's move on to next one. Okay, so here's another corollary. Let a prime b be integers. Okay, this means they are integers. If a and b are relatively prime and a prime and b are relatively prime, then a times a prime and also b are relatively prime as well. Okay, so this one we are going to prove. Before we to prove this corollary, there's one thing I would like to mention. So every time, right, every time you see a statement involving, the two relatively prime integers, right? Not always, of course, not always, but, likely that statement can be proven using this corollary. Okay, so in fact, this corollary is very important and comes in handy. Okay, very useful. Okay, so to prove that the corollary, let me get to my notepad. Let a prime and b be integers, right? And if a and b are relatively prime and a prime b are relatively prime, then a prime and b are also relatively prime. So that's what we are going to prove, right? So proof. Okay. Oh, there's something else I have forgotten. Now I remember, I usually like use different color for proof, right? Okay, so I mean it's not that important, but proof. Okay, so here we have these two assumptions, right? A and B are relatively prime, and A prime, B are relatively prime. So this implies, this implies, what is that? There exists, okay, I'm going to use this symbol. I believe I introduced this symbol somewhere, maybe not this course, maybe the another course, but in case I haven't mentioned this because I don't remember, but in case I haven't mentioned this symbol, this is what looks like a flipped E, right? That's it. Yeah, this is one of it, the well-known and widely used logical symbols, right? So what this means is there exists, okay? There exists or exist. So that's what that means, okay? This flipped E. Okay, so there exist uh, four integers: x, y, x prime, y prime integers, such that a x plus by equals 1 and a prime x prime plus by prime equals 1. So how do we know this? I actually applied, like I mentioned before, the preceding, the corollary, right? So in that case, A and B are relatively prime, so there exist two integers x, y such that ax plus by equals 1. Okay, so this is the corollary I applied. Okay, so let's get back to my notepad, right? So you know how I got this, right? Okay, so next step is I'm going to multiply these two guys, these two equations. So the ax plus by times a prime x prime plus by prime. If we multiply these two, that's still 1, right? So I'm going to put it here. So 1 equals 1 equals this, right? So this equals, I'm going to multiply these two guys out, right? And then, the right. So if you do, right, you get a times, okay, a times a prime x prime plus b times I'm going to have x y x y prime. Oh, I forgot something, right? So a x y prime, and then multiply these two. So when you factor b out, you get plus a prime x prime y plus these two. So 1b has been factored out, so I get b times y prime. Okay, you can write it this way. So this guy here, a prime x times x prime is an integer, of course. And also, these things right inside the parentheses is also an integer. So there are two integers, okay, such that a times this plus b times this, equals 1. So again, by the invoking the preceding corollary, right? By applying preceding, the corollary, we know that oh, I made a mistake here, right? Okay, actually, this is not what I wanted to write. Okay, I wanted to write a prime times xx prime, right? And xx prime is an integer. So again, by the same argument, right? And using the preceding corollary, you know which one I'm talking about, right? Okay, so what this means is a prime, and b are relatively prime. So this, completes the proof. Okay. All right. So next one is this theorem. All right. So if a, b, and c are integers such that a and b are relatively prime, and a divides b times c, then A must divide C. Okay, so let's also prove this theorem. So we are gonna go back to my notepad. Oh, there was a theorem. In fact, there was a theorem. Okay, so what was the statement? If A, B, and C, A, B, and C are integers such that A and B are relatively prime. Okay, A and B are relatively prime. And A divides B times C. Then A must divide C. Okay, that's it. Like I said earlier, right? Every time you see a statement involving, two relatively prime numbers, and you want to when you try to prove it, all right, always remember to try the corollary, right? I was talking about, okay? Since I'm not using corollary numbers, right? So let me get back to that. I'm talking about this corollary here, right? Okay. So again, like I gotta say, like there are exceptions, So not always, but likely your proof will work, may work. Okay, right. So let's go. Proof. Okay. So here A and B are relatively prime. So that implies that now I introduced or I mentioned, this logical symbol. So there exists. That way I can make, my proof like less wordy. So there exist two integers, x and y, such that ax plus by equals 1. Okay? So, we somehow have to use, this condition here, a divides b times c, right? To do that, we are going to multiply this equation, ax plus by equals 1 by c, okay? So that implies acx plus bcy equals c, right? Now, Uh, A divides AC, obviously. A divides BC by this assumption. So what that means is A must divide C, right? So here A divide A divides ACX plus BCY equals C. All right, so we just showed that A divides C. So this is the end of the proof. Okay, that's simple. Okay, not bad. Here's a remark. A divides, the multiplication of two integers, B and C, right? B times C, does not necessarily mean A must divide B or C, right? So here is an example, a counter example to that. 6 divides 36, right? Okay, and 36 is 4 times 9, but 6 divides neither of them, right? 6 does not divide 4, and 6 does not divide 9. However, the following theorem holds. If P is a prime number and P divides A times B, then for a prime number case, P must divide A or B, right? So we are going to prove this. This is actually, the very important theorem, among other things, and also very useful too, whenever like a prime number is, involved. This theorem comes in handy. Okay, so the statement is what? If P is a prime number, or in short, you can just call it A prime, and P divides A times B, then P divides A or P divides B. Okay, so here's a proof. So here we prove the theorem by contradiction. Okay, we did that before. Here also, we are gonna prove this by contradiction. So suppose, so negation of this is going to be, so suppose P does not divide A or changes to AND, right? When you negate, and P does not divide B, okay? Right, so that's the negation of this statement here. I gotta move to next page. All right, so here since P is prime and P does not divide A, so P and A are relatively prime. Okay, P and A are relatively prime. And what that means is there exist two integers x and y, where I'm heading at, such that px plus ay equals 1. Okay? And going back to, so when you prove a mathematical statement, okay, so there are things, you have to keep in mind. First, am I using, you gotta ask yourself, am I using all the conditions given? If you somehow prove the statement, the theorem corollary, the statement there without using, excuse me, like one or two conditions, then your proof is highly likely wrong. Okay? So there's one assumption I have not used is what? P divides A times B. So somehow I have to use that, right? Okay, keep that in mind. Another thing you have to keep in mind is where are you going? Sometimes, we have been doing mostly like a short proof so far, right? But when you do, especially like some like lengthy proof, sometimes, you get lost. Okay? You forgot what you are trying to do, right? Okay. So always remember what you are trying to prove, right? So where you are heading at, okay? Where is your destination? So keep that in mind. It is also very important. Okay, right. That will give you an idea, right? How to proceed as to, how to proceed with your proof. Okay, so in order to use that P divides A times B, what I'm going to do is multiply this equation by B. Okay, multiply this equation by B. So PB, so we obtain PBX plus AB y equals b. Okay, so you see that p divides obviously p times b, p divides ab, so p must divide b. Okay, so what am I doing? Since p divides p times b and p divides ab, that's by assumption p must divide b, but this is a contradiction, right? This is a contradiction. To what? Contradiction to our assumption earlier, okay? I assumed that, right, P does not divide A and P does not divide B. So it is it contradicts to this guy here, right? Okay, and why this contradiction happens? Because of this assumption, right? So the only other possibility is what? Therefore, P must divide A or B. Okay, so we finish it the proof, right? Okay. In fact, in this case, there is essentially same proof, but you can write the proof in a different way. So what we just did is, proving the theorem indirectly using contradiction. But there's a way you can prove the statement directly, okay, without going around by, assuming the negation of, the conclusion. Okay, so here's a second proof. Two. This is a direct proof. Excuse me. You know, it's not always possible or easy to come up with the, different ways of, the proving the given theorem or corollary, like a certain like a mathematical statement. Okay. Often, like what the contradiction, proof by contradiction, is much easier and shorter than direct proof, and also quite often, direct proof of a certain statement is extremely difficult. Okay, extremely difficult. Right. So it's not always, the like I said, easy or even possible, to come up with like a different, ways of, the proving like a given statement. But in this case, yes, right? And when possible, and also when it's feasible to do, right? It is actually very good practice of writing proof, in different ways. Okay, so to try that. Now, so like I said, this is actually essentially the same proof, but here we go. So with all like given assumptions, right? Okay, if so, we are trying to prove that P divides. Okay, so if P divides A times B, then P divides A or P divides B, right? Okay, so yeah, maybe I should write that down. So suppose that P divides A times B, right? And we want to show that P divides A or P divides B. So if P divides A, then we are done. Okay, we are done. There's nothing more to do if P divides A. Okay, already, that satisfies the conclusion, right? If not, if P does not divide A, then since P is a prime, P and A are relatively prime, so that implies there exist two integers xy such that px plus ay equals 1. Okay, and you know the rest of the story, right? So we have to use this assumption here, P divides AB. To do that, I'm going to multiply, oh, come on. I'm going to multiply this equation by B. Okay, so PBX plus ABY equals B. And since P divides P times B, obviously, and P times AB by assumption, so P must divide B. This is it. Okay, this is it. And you know, you might also ask why you start with like P divides A. Well, then you can start with P divides B. So, you know, divides B. If P divides B, then we are done. And if P doesn't divide B, then by the same argument, you can also show that P divides A. So it really doesn't matter, okay? Right. But that's a direct proof, right? So again, you know, the core, the idea is the same, right? So essentially the same proof, but earlier one is indirect proof by contradiction. This is direct proof, okay? Right. So, you know, just a different way of writing a proof. I think this is, you know, a good point to stop, good place to stop. So, uh, I will continue, you know, our discussion in my next lecture. Thank you.